Oops. All right, so let's say, for example, we have a spring. We're going to attach a mass to the spring like this. And if we start at our initial position, let's say x equal to 0. We actually have a name for that position. Is it just me or is this blurry?
It's a little bit.
Can't tell if it's my eyes or not.
That's cool.
All right, so at this x equals 0, what do we call this x equals 0 position? Equilibrium, our starting point. This would be our equilibrium state. So anyway, we're going to go ahead and stretch the string. So for example, if we grab onto this with our hands, pull it with the force this way, we can stretch out the spring, right? We can pull it this way. Let's pull it, say, a distance x, or let's call this x max here. So anyway, as we start pulling on the spring, what's the spring going to do? It's going to pull back, right? So the spring's going to stretch out, and as it stretches, it's going to start pulling back. Now what happens to the pulling force of the spring as we pull farther and farther? It increases, right? So if you can really feel this with a rubber band, if you have a rubber band, as you pull it back farther, what happens to the force of the band pulling back? It increases. It gets harder for me to pull back, right? I have to pull back with more force, and the restoring force from the rubber band also increases. So as x increases, that force going back also increases, okay? So anyway, when we reach this, say, maximum point, if we call this F max, then the spring is going to pull back this way. And if this is not moving, right, what should be true about those two forces? They should be equal. So the restoring force will equal whatever my maximum force that I apply to this is. Okay? So we could derive the equation for F spring. So what are the two factors that would affect how hard the spring is going to pull back? Okay, so one would be the distance, right, which we just talked about. So as x increases, then that force pulling back is going to increase. The force I have to pull increases, and the force coming back would also increase. So we call this simply x, right? And then what's the other factor? Okay, the spring constant. So this would be the distance that we pull, and then the spring constant. Anyone remember the symbol for that? So it's called the spring, or your book uses force constant. And really what this is, you know, what the spring's made out of. More or less it's how stiff it is, the stiffness of the spring. So as K increases, the stiffness of the spring is going up, or as the stiffness goes up, K would be going up. What are the units for K? You could derive it, so this would be K times X. You could derive the units, right? We want to end up with force. What's the units for force? Newtons, and we have X here, which is a distance, or meters. So what should our units for K be? Newtons per meter. Okay, newtons per meter. So for example, if I had a spring constant of 100 newtons per meter, that just means if I pull it back 1 meter, how hard is the spring going to pull back? 100 newtons. Or I would have to exert a 100 newton force to pull the spring back 1 meter. If this goes up, then it's harder to pull it back, right? You'd have to use 200 newtons to pull it back 1 meter. One last thing we're going to do with this, notice in our picture, X is going this way to the right. However, what direction is the spring force? To the left, in the opposite direction. So this equation, when you see it written, you'll see it written like this: F equals negative kx. And that just is telling you the direction. It's a restoring force. The direction is opposite of what x is. So if you go x to the right, the spring would be to the left. If you go x to the left, the spring would be to the right. Yeah.
If you do newtons divided by meters, would you cancel the units and do kilograms over second squared?
If you want to break this down into the pure units, then yeah. But we usually write it. It means more to us to write it as a newton per meter than to break it down into the mini units. All right. So anyway, that's our thing for springs. So let's go ahead and do a problem here.